Have you ever really stopped to think about how thousands of people in a city can all be on their cell phones at the exact same time? I mean, how do all those signals not just crash into each other and become this one giant, garbled mess? It's a huge challenge in wireless communication, and to really get how we solve it today, we've got to go back to the very first solution.
Think about it like this. When you're driving around and you tune your car radio to, say, 98.5 FM, you only hear that one station, right? The station at 101.0 FM doesn't bleed through and mess it up. Well, that simple act of just tuning to a specific frequency, that is the core idea behind what we're talking about today, frequency division multiple access, or FDMA. So, how does that radio analogy actually apply to something like a phone call? How do we let a whole bunch of people talk all at once? Well, it all comes down to how we slice and dice the airwaves. Let's just break down the name, because it tells you everything. Frequency division. Okay, that means we're chopping up the available spectrum. And multiple access means we're doing it so that lots of people can get on the network at the same time. You can picture the wireless spectrum as a giant highway. FDMA's whole approach is to paint a dedicated private lane for every single car. The second you make a call, you get your very own lane and nobody else can use it.
The process itself is surprisingly simple. First, the system takes the total chunk of spectrum and divides it into a bunch of smaller channels. Then, when you start a call, you're assigned one of those channels. And here's the absolute key. That channel is yours, and only yours, until you hang up. And finally, to make sure nobody's signals get crossed, the system leaves these little unused gaps between each channel.
And those little empty spaces? Those are called guard bands. Just like the painted lines and the space between lanes on a real highway keep cars from bumping into each other, these unused gaps in the frequency keep your phone call from bleeding into someone else's. It's a really simple but absolutely vital trick to keep everyone's conversation clear.
Okay, so it sounds like a pretty clean and simple solution, right? But that simplicity comes at a really steep price. Let's take a look at the good parts and the pretty significant bad parts of this whole approach. So here's the big trade-off. On one hand, the design is super simple. You get a dedicated channel, so there's no waiting and very little delay. But the disadvantages are huge. The absolute biggest problem is that it wastes a massive amount of spectrum. I mean, think about it. Not only do you have your own private lane, but those guard bands are also just empty, wasted space. The whole thing is just incredibly inefficient.
Let's really dig into this whole wasted spectrum thing, because it's the real killer. A normal conversation is full of pauses, right? You've got moments where you're just listening, not talking. So what do you think happens to your private dedicated frequency channel during those moments of silence?
Exactly. It's completely 100% wasted. If you're silent for 10 seconds, that private lane on the highway is just sitting there totally empty, but nobody else can use it because it's still assigned to you. That right there is the fundamental, massive inefficiency of FDMA.
Now, this isn't just some old theory in a textbook. FDMA was a real technology that powered the very first generation of mobile phones. So let's see how this actually played out in the real world.
FDMA was the absolute backbone of 1G, the very first generation of analog cell phones. Yeah, we're talking about those giant brick phones from the 1980s. Every single call made on one of those things was given its own dedicated frequency channel using this FDMA system. It was also pretty common for satellite communications for pretty much the same reason. It's simple and it's reliable.
So, knowing all these limitations, how many people could a 1G system actually handle at one time? Let's just look at the raw numbers to see the real scale of the problem.
The number is, well, it's pretty tiny. A typical system with a standard chunk of spectrum could only support about 1,200 simultaneous calls. That is it. In an entire major city, only 1,200 people could be on the phone at the same time. You can see right away why this technology had a very short shelf life.
All right, so we've covered the mechanics, the pros and cons, and where it was actually used. So what's the final verdict? What's the big takeaway on FDMA? So here it is in a nutshell. 1. FDMA gives every single user their own private frequency band. 2. It was simple and it worked, but man, was it wasteful. And most importantly, number 3, as inefficient as it was a necessary first step. It was the foundation that all of our modern wireless systems are built on today.
And that really leads us to the big question that drove everything that came next. FDMA solved the problem of letting multiple people talk at once, sure, but it created this massive new problem of inefficiency. The challenge for the next 30 years of innovation became crystal clear. How do we get smarter about sharing this resource? How do we serve not 1,200, but billions of users without wasting our most valuable and visible asset, the airwaves?